Hello and welcome, everybody. So this is us. And this is one of the instruments that, that I love. It is so helpful and meaningful. And although we touched on this in a more comprehensive way with our science faculty partners, Christine was there, and Hanley Ardendorf and a couple of the others, and Max Blackie on using the epistemic plane in a slightly different way. Today, we're actually going to zoom right down, right in, and see what this does in engineering and how we've done this. So just for context, for those who don't know us, we're down at the southern tip of the African continent, and this is a research-intensive institution in South Africa, and the Faculty of Engineering has around 4,000 students. That's 3,000 undergrad and 1,000 postgrad. And what research intensive means in our context, although there are a number of us, is that means traditional. We are recording, so I'm going to use the word traditional, as in the Humboldtian 150-year-old standard, staple, solid, the Bernsteinians, singulars, which then get moved into later in the program to these kind of regions, the 5 engineering programs that we teach, but all our undergrads do the same common first year. So we're really active. I know I called us the Stellenbosch LCT Group. I don't think the others would see us as that. We're just the Recommended Engineering Education Practices Group, and LCT has been really amazing in helping us tackle a whole lot of challenges. Key challenge being the complexity of a region like engineering and this constant need to connect theory to practice in a way that answers the demands of the 21st century, which are actually really quite radical. So I've used this graphic before. Those of you who know my work will know this. UNESCO has a really, really nice definition of what engineering is. And engineering is STEM. It is science and technology and mathematics. And if you added the Americans' STEAM, you know, the arts element as well, you've got a whole lot of different kinds of forms of knowledge with the implied and associated different kinds of knowers that you're now trying to bring together basically to solve socio-technical, socio-economic problems for society. So we do know that working in this space means you need to, in these terms, recognize different kinds of phenomena and their fixed, respective, or other possible approaches in these different socio-technical contexts. What we also know from my own research and from how we've extended this is that successful engineering practitioners do this. They recognize these different kinds of phenomena, when it's a natural science principle, when it's a mathematical concept, what kind of tools and technologies, in what kind of context, in an iterative, non-linear fashion. In other words, there's this constant movement, this shifting. We call it code shifting, but it's continuous code shifting, and it's not necessarily linear. So let's go to our wonderful instrument. This is a little blurry, but those of you who do know this instrument will recognize the principle here. We're talking about differentiating between the what and how of a knowledge practice. So this vertical axis, we've avoided using the kind of really more heavily theoretical or conceptual terms in our context. But for us, that vertical axis, go for it.
You really should, you get me to send you one without the smudge in the middle.
Yes, okay.
And nice.
It's actually a good idea. You can actually upload all of them to the website, and then we can use the one without the smudge.
I think
keep reusing
that
slides.
Is on the website, actually. I think it's on the website. Yeah.
Okay.
There you go.
What does the smudge actually mean? Why is it there?
Let's not go into that. That's now historically gone.
Okay. But I think the smudge, I'll tell you what it does mean, and Carl will appreciate this, and he's going to show you this in a moment as well. It's degrees of, I don't want to use the word density, it's degrees of difference. The smudge suggests another axis. It suggests
well,
the z-axis.
I mean, just to answer the question then, it's because I had a real problem with, when I first started doing this stuff, that the most of my audience were people who come through like Bernstein's work, and they just could not get their head around continua. And
right.
so I had to, it was one of the ways in which I kind of nudged people to understand that these were continua. This is a topological space of the infinite positions, rather than 1, 2, 3, 4. Typologies is 99% of the Bernstein and post-Bernstein work has been with like 1, 2, 3, 4 typologies. So it's like trying to get them to think in terms of planes, which is the biggest revolution in LCT. It was very hard. So that's why the smudge was there for quite a while.
Yes. And in fact, that explanation is great. And so I'm not going to change it. I'm going to leave it. We'll recreate the smudge in a way that does suggest exactly what we've been trying to get to, that there are degrees on the z-axis, basically. Okay, so the vertical axis is about what we call ontic relations, and it's the boundedness of a phenomenon. When a phenomenon is strongly bounded, as in moving towards the top of the plane, we talk about it being, well, we do in our context, as being almost not negotiable. It is what it is. You recognize a thing. The thing is a thing in itself, irrespective of what you call it. You recognize that phenomenon as being a strongly bounded phenomenon. And what's useful is that in the natural sciences, all the kinds of fundamental phenomena, like a kind of force or gravity, or those tightly bounded phenomena. When we move down that vertical axis, we start becoming either more ambiguous, more contested, or more weakly bounded. You'd need a whole lot of other things to ensure that we're all on the same page about what we're talking about. When we go to the horizontal axis, it's about how we're approaching that phenomenon. The more tightly bounded it is, as in fixed approaches, as in not negotiable as well. We're on the right-hand side. Discursive relations, how we talk about, how we approach this particular phenomenon. As we move out towards the left-hand side, how we approach something becomes more open-ended, allows for other kinds of possibilities. So what we've done is, this is our sort of go-to translation device. Those 4 quadrants, and I want to point out again exactly what Carl has just said. Although these are descriptors of those 4 quadrants, the point is they're about what we call kinds of insights, ways of thinking, and the thinking stretches, moves, shifts. But in that top right-hand quadrant, when you've got stronger ontic relations and stronger discursive relations, you're talking about engaging in a knowledge practice with what we call purist insight. Insight that is, the phenomenon is clearly bounded, the approaches are quite straightforward, and we all, in our field, well, in engineering, teach around those. The core fundamentals, all those natural science things sit up there. Standardized equations, standardized formulas with these uncontested phenomena. When we move down to the bottom right, it's about, this is now no longer about the phenomenon itself, but it's the practice itself foregrounds a particular procedure that is accepted by the field as a whole. And all that stuff on the right-hand side is the stuff that you're going to find in engineering textbooks world over, irrespective of their language. Here is a shear force, here is a bending moment, this is the equation. We're all going to do it at some point. Where you put it in your curriculum is a different matter. Now, as we move to the left-hand side, top left quadrant is, the phenomenon is exactly the same, but how we're now going to approach it can vary. I can tackle it with a different set of tools, or with a different kinds of language, or multiple kinds of language. And I'm thinking of the verbal, visual, symbolic, which each of them can be require doctrinal insight on the right. But when I start pulling all of these together and open up how I might approach something, we're sitting on the top left-hand side. And when I pull that down to the bottom left, it's contextualized anchored quite possibly in terms of in relation to the stakeholders in the space, the knowers in the space, different kinds of students coming into our, let's say, engineering program with different kinds of perspectives on or conceptions of a phenomenon. If I draw on those things, then I'm actually looking at kinds of knowledge practices that are orientated towards that bottom left, okay? I've jumped the gun a little because my colleagues are going to tell you about that. So what's important is that you can see that some of that original UNESCO graphic about the field we're in, some of our knowledge forms, okay, kinds of knowledge are orientated naturally. Their kind of dominant insight is according to those different quadrants. It's very important that you know that if you separated out each of these knowledge forms, you can play with it across and around, moving around the epistemic plane. It's just that their dominant orientation sits in those positions. Your physical sciences or natural sciences, mathematics, what we've called logic-based sciences because of engineering and technology, sit over there. We've ignored the know insight because what we're doing is taking our knowers, our students, ourselves, the people responsible for these phenomena into account. So we've got a knower orientation to that bottom left position on the epistemic plane. Now, in our case, what's really been useful is we've labeled these to make them accessible to my colleagues and people beyond this group over here as principles, procedures, possibilities, people and places, because those things then start to echo what we see in our graduate attributes and our standards, the kind of the discourses and the languages over there. That's helped us to bridge the space between LCT and social, well, and sociology of education kind of language and stuff that you're finding in your curricula. Now, just
can I butt in?
Yes, please.
Can you go one slide back, please?
Yeah.
So it's interesting that logic-based sciences, that's engineering, right? If I remember correctly, which you mentioned. So it's interesting that you move it as predominantly in the situational insight quadrant, where, I know some of your earlier work where you looked at how engineering graduates going into different workplaces, right, had to either adapt to what was expected of them, like a particular company perhaps expected purist insight and others doctrinal insight and so on. And some students adapted and some not, right? So from that work, my impression was that engineering did not really sit in any particular insight quadrant, but really depended on context.
Okay.
So now
you've asked a very important question. All of this is engineering. So the whole plane is engineering. The logic-based sciences are actually the technologies, because the technologies are all things that are designed. Every single tool we use initially starts out by being anchored by a fundamental natural science principle, what a material is, what it can do, etc. And that is determined by the mathematical relations between the properties of a material or the all the other elements that go into a tool or technology. Now you just expand that into the computer-based technologies, and now you have a myriad of possibilities. Every single cell phone and the traditional telephone and me talking to you like this, those are all the different kinds of tools. They're logic-based tools. I can choose any one of those versions to fulfill, to address the phenomenon of communicating with you. So in other words, the top left quadrant is merely representing the tools and technologies employed in engineering, but the whole plane is engineering. So maybe okay. So that's the tools and technologies that we use with the mathematical sciences, underpinned by the natural sciences, what is possible, in terms of force and heat and all of those other things. When we pull those all together, yes.
No, when you're done, let me pop in. When you're done with,
no, go for it.
So I just want to make sure I'm understanding the difference between purist and situational insights. in engineering, there are sometimes purist principles, but you can choose different ones. So you've got this kind of semi-open-ended approach, but it's actually it's an alternative between fixed approaches. Would that stay in the purist or doctrinal site? And then you're speaking in terms of the situational insight, you're talking logic-based sciences. I shift across into civil engineering, which is, I would presume it's in the same space, but I was just interested how you would define that as a logic-based science, not being logic in the computer sense.
So what I was going to say, the original naming of that as the logic-based sciences came from the computer. It came exactly from there, with the Boolean logic issue, with in terms of the moment you bring a computer into a space, you are setting up a decision tree that you decide on, but it's governed by, it's a constant iteration by, but hang on a moment, can these electrons flow in the circuit that I'm constructing? So it's always the fundamental principle is whatever the natural science principle is that governs it, electromagnetism, thermodynamics. In other words, each of those, there are principles, which we keep calling principles, that require purest insight. You need to understand the relationship between pressure, volume, and temperature, for example. That will govern it. But what I do with it in the system, I make a decision about putting one thing in relation to another thing. So in a sense, what we're talking about is design. Design sits in the top left. Which is why it's important that Carl pointed out right from the beginning. We may be locating these things in a quadrant just to help anchor the kinds of things we're talking about, but it would constantly be this iteration. So if you're talking about a design principle, if the design principle is about, I don't know, give me a design principle, it might still sit in the situational insight quadrant because you may have several design principles. You're just choosing one, but that principle would still be governed by a natural world or whatever phenomenon that is uncontestable, that is what it is. You can't do X with Y because the laws of nature.
So sorry, just to confirm, so if I talk about there's this abstract problem that you can use a Newtonian method to solve or an energy method to solve, that's still staying in the principle space, that's still staying in the purist space.
Yes.
So you've got alternatives, you can do it in different ways, but it would be in that space, just possibly closer towards the axis.
Yes. And in fact, what you would do, you'd move down into the...
Talking about, sorry? Now
and
we're talking about... Go, Karen, I'll shut.
I just wanted to say, you gave me two beautiful examples, which would pull you immediately down into the doctrinal quadrant, because the Newtonian method is X, irrespective of, do you understand? So you're moving anyway in that simple thing that you've just raised as an example.
But would it, no, okay, so the phenomenon has changed, and the phenomenon being energy versus Newtonian, as opposed to the thing that you are analyzing.
Yes.
Sorry, I'm so slow on this. The thing that you are analyzing, is that OR or DR?
That's the whole plane. That's the dot in the middle. I always said this is the problem being solved, is where the two axes meet.
Well, I think what Nikki's asking about is the objective study.
Yeah. That's
Can I jump in?
Please do. Go for it, Robbie.
So the way that I think about it, Nikki, is if I give an engineering student a problem like, we've got water, we want to pump it up the hill, that's very situational, because the thing that you're studying is well defined. I know what I'm doing. I want to make this transport happen. From that situational, we then go into the purist by saying, in order to do that, I need to understand Newtonian motion, I need to understand energy and all those kind of things. And I use those tools in order to solve it. So it's well defined, it's OR plus, it's strongly bounded. If I said something like, you know, we've got to make life better for people, that's it's less bounded. Like there are multiple ways that you could do it. There are multiple facets to that. So that's a less well-bounded phenomenon that you could then approach by saying, using specific tools and move them onto the right-hand side for the DR plus.
So are we talking about like tours, just like in autonomy, you're moving from one kind of insight to another, as you're solving one kind of problem?
Yes, right? That's exactly what we're talking about. And you're going, Nikki, I was going to say, let the others show you. Okay, let them talk through. So Robbie, Coral, and Neo are going to show you how they've used it, and I think it'll clarify some ways in which we're seeing this.
Great, and then let's get on to that. But Corin, I have a question that's always sat in there, and Pavel puts it. What is actually the difference between this and autonomy? So, but I think that's probably a later question, but I want to jump in now because you talk faster than me. So, yeah.
That's like asking what is the difference between this and semantics. This one is not who's doing it and how strong it is, but sovereign is definitely has a good relationship with purist in terms of the two planes. You know what I'm saying? There's a that's simply because of the way.
Do not speculate about the relationship between two dimensions. They are absolutely, consider them to be separate theories effectively. That is an empirical question. So it's like, but they are so different. It's like this only appears through having done specialization. You're looking at epistemic relations. So it's got nothing to do with the thing is though that empirically many of the same features so an empirical characteristic or feature or something like that can be analyzed for its autonomy and its semantics and its specialization and later on its temporality, and the same characteristics may be indicators of those different things, but they are looking at very different things here. I mean, like this is nothing to do with constituents and how they're arranged, which is all that's about.
I can see where Nikki's question is coming from though. So just park it for a second, Nikki, because it's a very important thing that you have raised. But but it's also because of the Cartesian plane. So all we know, to go back to what Pavel has noted then, is just these are a couple of the pictures, the simplified pictures of those, what you're calling tours, but are code shifting practices, where starting at any beginning points and traveling around the plane are examples of practitioners in different kinds of engineering practice sectors and what kinds of knowledge they were drawing on. Okay, that was the color coding. You can't really see it, it's quite vague, but the green was always the sciencey stuff, the red was always the mathematics, the blue was the logic-based stuff, and you can see those colors crop up in all the different insights. In other words, people were using what we said was naturally orientated to one of the quadrants in a sense, but in different ways as they solved a problem over time. So we know from those patterns, those are three fundamentally different kinds of sectors, that different kinds of problem solving, code shifting happens that is really context bound and context, well, that is more impacted on by context. So our big challenge is how do we enable or design for or see these code shifting patterns to produce the so-called engineering graduates with these more complex abilities in a more complex world in which we are. And that was the kind of question. So if we I put them into the different quadrants as well because it made sense to me at the time, but I found myself, Robbie, questioning. So I've got you in this purist, from a purist insight perspective, and I think that's relative to our context of this traditional fundamental, this is the curriculum, this is the structure, this is how we work in our space. We've got Robbie up front first talking about designing the pedagogic experience. Then we're going to open that up to how, with the epistemic plane, to Carl looking at code shifting, a beautiful code shifting strategy. And then we're going to move to Neo, looking at how our students code shift in a particular context. Right, so can I just go to you, Robbie?
All right, thanks. I'm going to be relatively brief, seeing as Carl and Leo have much more interesting things to say than me. But so I teach second year fluid mechanics, and this is one of those areas where students find it particularly difficult because they come from first year where they are given very, not simple, but well-defined questions to do. So in mathematics, you're asked find X, and then you've got to do the mathematics to find X. And implicit in the question is the solution methodology. Even in the engineering space, you know, we give them a simple mass balance and say this stuff comes in, how much comes out? The reaction is this. What is the answer? And in fluid mechanics and in the years that follow, what you actually start doing is giving them a range of tools and then a situational problem that they then have to pick the correct tool and apply in the appropriate way. And we kind of assume that the mathematics is trivial by that stage, and it's the choice of the right tool and applying the right kind of thinking that is then the useful thing. So the next couple of slides, what I've done is just trying to think about the kind of interactions that we have with students and the things that we do with them, and where those activities sit in terms of our context and you know, are we purist, are we situational or doctrinal and so forth. So if you think about lectures, in the kind of way that we lecture is, here is the Navier-Stokes equation, this is the way that you apply it, this is how we derive it. So we're going from very purist principles, drawing from mathematics, drawing from the physical sciences and Newtonian physics and so forth, and clearly outlining how one uses it, how one sets it up. Every now and then we'll say things like, you know, we would apply this in solving fluid flow in a pipe or solving fluid flow in a reactor. And so that's drawing some situational threads, but for the most part, it sits very on the right. The kind of approach that we want is very well defined. And we walk through it systematically in the lectures. If you can go forward on that. Mm-hmm. Then the other classical thing to do in the classroom situation is, okay, well, now I've shown you how I derived the Navier-Stokes equation or Bernoulli's equation. Here are a bunch of questions. Go and practice. And in those kind of situations, what the students often do is they sit right down there at the bottom in the little red square of, they recognize the shape of the question and they reproduce the kind of calculation or approach in an algorithmic way to get an answer. And that's not wrong. It's a good way to learn how to do something. But what it does do is students who sit down there and are only able to recognize a question based on whether its shape is well defined for them and follows one that they've seen before, means that they're not flexible, they're not able to then apply the same kind of thing elsewhere. The better students are able to say, oh, I know why I'm doing this kind of calculation here. It's because it's a laminar flow system and the equation that we derived comes from the laminar flow system. So you see how it like pulls up towards a more general principle rather than specific. But a lot of them sit very down at the bottom. And that's a concern for me as an engineering educator, because they then are unable to take on a general situation. So Nikki's question and Pavel's question were both on, and Christopher's in the chat, were along the lines of, okay, but isn't that what engineering is? Don't you just, you know what kind of problem it is and you just solve it because it's well defined? But of course, that's not really the case. In industry, sometimes we don't know what the correct solution is, or that we should be applying Navier-Stokes at all. Do we even use fluid mechanics? So for instance, if we are thinking about, are we going to build a mine on the dunes in outside Pott? The engineering solution is, okay, we design the mine. We figure out is there ore in the sand? How do we get it out? How do we transport it? You can see how situationally we're now putting across to a purist principle, transportation systems and separation systems, and you know, all the technical stuff. But the situational question is, do we build a mine? And one of the ways that we can approach that is, will we make money when we build the mine? Some of the other ways that we could think about, should we build a mine, is what does the local population think about us building the mine? How do we have community buy-in? What about market instability? Like, the stuff is now valuable, but is it going to be valuable in 10 years? So you see, so the engineering problem is not just one of
Robbie, are those engineering problems, or are they problems for sociologists, for economists, for ecologists?
Well, these things are not, shouldn't be siloed. The engineer has to also answer those questions as well. I mean, yes, sure, the economist also answers the question of, you know, is it worthwhile doing? And the anthropologist or the sociologist goes and talks to the community. But as an engineer, I also need to have access to that knowledge, because the question of building or not building is one that I as an engineer have to answer. And the way that I approach it changes based on the answer to those questions. So a weird example, one of my colleagues recently went to a mine, and you can automate many of these things. So there's a big electrowinning facility. It's full of highly corrosive sulfuric acid. It's dangerous to work in. It's a horrible place. We don't want to have people inside there. And yet the mine will not automate it, because that would mean firing someone, and they can't do it. They cannot fire that person because of the implications on the community. If they fire that person, the community will be up in arms, and then they won't be able to operate at all. So the design question of how do I design the system, the obvious answer, the purest answer is automate. And then we can go down into the doctrinal and figure out how to do that. But the situational answer is, you can't automate. I have to choose a different route to solve that problem because of the situational aspects to it. And then I choose a different doctrinal route of, okay, well, I can't automate it. Let's design for safety. And then I do a different kind of thing in the electrowinning facility.
Okay. Robbie, maybe I can just add, sorry, Paul, just to add to Robbie there. I think for engineers, it's about the awareness of decisions. So not necessarily the answers, and Paul, I think you referred to that, where there are other role players and other experts that could be involved in answering that, but engineers should at least be aware of the fact that there are decisions to be made. And that's the big difference from engaging with problems in tutorials or assessments where the decision, there is no decision. Essentially, the question guides you to applying a certain procedural principle. And yeah, that situational quadrant is all about realizing that there are decisions to be made, and of course understanding that.
Right. So yeah, so that's kind of what I meant. I kind of get that impression, maybe a false impression, that that all the decisions kind of rest on the shoulders of engineers, where there are other specializations or people who study other things who should weigh in, right? And of course, engineers should be aware of those
and pull on that expertise and take on board that. I mean, the engineer would never think about, oh, we can't do this clearly optimal, really clever automation thing. Obviously, the engineer is going to be like, that's the solution. It's the most optimal one, it's the cheapest one, it's the safest one, we should do that.
But not the chemical engineer.
Yes.
Even 2000, I was trained in chemical engineering, and most of our fourth year was this consideration. So the process engineer has to consider that. So just saying.
Yeah. I mean,
Chem Eng does this
important.
anyway.
Yeah. Robbie, I just wanted to maybe anchor this for Pavel again and ask a technical logistical question. Carl, you got a lot of slides taking us through sequence. Can you present your own slides? So will you take over sharing when we come to your section? Is that okay? All right, cool. What I wanted to say to Pavel as well and the others that might be asking, if just to go back, is that so what we've done here is the epistemic plane has given us a way to consider from our traditional kind of engineering program, where they have 3 lectures a week, they have probably 2 tutorials a week, the focus is on different things, then a prac or project-based work fed in. What we do through that cycle is we move from the fixed and more, or the tighter, the more bounded elements in a kind of a traditional way, and have started opening that up by stretching the students outward within a program in terms of how we structure lecture, tutorial, practical, and possible project. Because our biggest challenge is over the program, how do we shift them more and more left? How do we open up their possible approaches while anchoring those fundamentals on the right-hand side? How do we stretch them there? Because industry keeps on telling us too much focus on the right-hand side and all these solid, not negotiable stuff. Our graduate, not our graduates, but engineering graduates as a whole, across programs, can't solve complex problems. They're overwhelmed in the real world with exactly what Pavel asked. You know, these really complex, stakeholder-y orientated, different perspective issues. And internally in our faculty, we're trying to use this instrument. Well, we're trying to develop strategies to stretch our students, to enable them to start thinking in more open-ended ways. That's kind of where this is coming from.
Just out of curiosity, so of course this, what you're talking about, involves literally mind change of students, right, who are taking this degree. So they'll come in with a particular idea of what engineering is and what they expect to do, and suddenly you're exposing them to something they might be resistant to it, right?
Yes,
so how
very
has this
resistant
been?
to it.
Yeah,
they're very resistant to it. So I mean, I was talking with Debbie Blaine yesterday about, she recently got feedback on a very similar kind of thing, asking an open-ended question in an exam or something like that, and the student feedback was, I can do when you give me the problem and I solve it, and I do well at that. That I can do. This is what the students are saying. And they feel so comfortable there because they can do the maths, they know the shape of the problem, they can solve it. It looks very much like school. And then when we take them up to the top right-hand quadrant and give them this open-ended assignment, and this is what we do in finding a design, it's super open, like it's one sentence and that's supposed to take them 6 months. It's a huge problem, very situational. They resist it with a lot of their being, but they need to have that mind shift. Because
what about people from the management, for example? Do you have support for that, or is it just, well, I say just like initiative of a few lecturers or professors, but if the management's not behind you, right, and or if other professors, lecturers do the traditional way of kind of keeping engineering on the right side of the quadrants, not that they even know what those quadrants are. But I mean, you need support, right?
But they don't know what the quadrants are necessarily, but there's general broad support for moving towards situational. But there's always, I mean, asking questions on the right-hand side is super easy. You just take them from the textbook, and then it's very well defined, and marking it as easy because they either get it right or wrong. It's a balance. But I see Rita's got her hand up.
Thanks. I just want to make sure that I understand this properly. So, like, if I could bring an example, let's say, like, we have a problem that's like one of these big, undefined, you know, let's like things that are generally called like wicked problems, right? So, like, you know, world hunger or something like that. So, if you were to say, okay, we are trying to solve this kind of problem, we've got people working on this from all kinds of different angles with different methodologies, then I'd say that you'd be working with, you know, like, let's take it as the kind of biggest, broadest example. You've got people who are like sociologists, and you have humanities and engineers and everybody trying to work towards this problem. Then you've got a really good example of weaker DR, right? Where the methodologies are open, and you are trying to solve a problem. But now the problem is also not very well defined, and everybody is going to construct that problem in a different way, and how you construct the problem will make a difference about how you go about trying to solve that problem. So then my question is, if you are in that, are you actually in that situational insight then, or are you actually in the the knower, because it's, you know, because the problem isn't well defined. And what you were saying, Robbie, sounded to me like you're starting to talk about things where problems are not well defined, and I'm just wondering if that is OR plus then, or if it's a matter of moving out of the knower insight into constructing the problem in the situational, and then only you know, drawing on your methodologies to solve the problem.
Yeah, you're right. If the problem is so nebulous that we're not even sure of the kind of approaches one could take, and it depends on the kind of person you are as to the kind of approach that you take, then definitely the ontic relations are weakening. Yeah, and I mean, we must remember this is not it's either in that box or it's in that box. It can be more or it can be less. It's a comparative thing. It's a gradation. Carl, maybe you have something to add to that.
I'm just also cognizant of the time, so I was going to say, Carl, you can take over.
Yeah,
I'm stop
done.
sharing, and you can take over, but we're continuing the conversation.
Yeah, so maybe just to just add on to what Robbie said, there may be one perspective on that, is that in the contextual or knower quadrant, essentially the problem is undefined, and once the problem has been defined, and at that stage you'll find that the solution is undefined, that's when you're in the situational. I mean, that's where an engineer has to reflect on the tools that he has, the approaches that he has to his disposal, to be able to engage with the problem. All right, let me share my screen and also lower my hand. Okay. Okay, Karen, can you see?
Yes, perfect. Go for it.
Okay, so as Karen mentioned, so moving into or using the epistemic plane just as a tool to structure the presentation, essentially moving on to my side now. That's essentially the idea of what are the possibilities, the situational considerations for using the epistemic plane in our engineering education, our teaching and learning. So that's where I've applied this, try to make sense of it, try to put it to use in my teaching. So yeah, my works is essentially, I thought it just in terms of a title, it's enabling epistemic transitions. So I think Pavel mentioned the concept of tours. I think that's very much related to that. So transitions on the epistemic plane, and how I've applied it, and what I will use as a essentially example to explain my interpretation of this is by integrating virtual and laboratory experiences in my third year mechanical and mechatronic engineering class on control systems. So when I started to actually discuss these things, and also early in my career already with Karen in terms of what do we need to do in engineering education to improve things, to deliver better students that are better problem solvers, that are more adaptable, that are less bounded within the purist and doctrinal quadrants in the way that they engage. I worked on the idea that what we want to improve, for lack of maybe a better word, is a holistic learning experience. So the idea is that students engage with problems, and we can also say that students gain insight in different ways, and that's essentially what we can map to the epistemic plane, which we've discussed I think in enough detail to this point. But yeah, so due to my obviously lack of experience and knowledge on this field, at the start of this journey, I tried to make sense of the LCT, the theory, the epistemic plane, and essentially how we could apply that. And essentially my interpretation of that, it made more sense to me to actually characterize these quadrants as learning or engagement actions. So essentially what I did is I just took those quadrants and just by changing the wording, represented them as certain mechanisms or actions of learning, of engaging, of gaining insights. So just so essentially the quadrants are then understanding principles, applying procedures, identifying opportunities, and considering context. So that's essentially just it's exactly the same meaning as what we had these quadrants earlier, but this was my interpretation and trying to put it into more actionable terms. So what we then also did is we added an extra dimension to the epistemic plane, and Karen did refer to this earlier, and this extra dimension is essentially, again, for a lack of a better word, complexity. All right, so and we've indicated that on the epistemic plane is essentially a distance from the origin. So we could assume that when these learning actions occur in terms of the epistemic plane closer to the origin, that's when essentially the level of engagement is simpler, and the further that we can map that specific engagement away from the origin, that should represent a higher complexity, more sophisticated engagement. And then, the idea is that if we want to enhance this holistic learning experience, then we can support
Carol,
to achieve that.
What do you mean adding another dimension? Are you talking about adding another axis?
Essentially, yeah. So it's essentially a third dimension to this idea.
In other words, it's not
another
challenging,
axis.
stronger. Yeah, it's not those arrows. You must see it in 3D. Those arrows are not moving, strengthening ontic and discursive relations, for example, or weakening them. It's a different axis. It's trying to accomplish what your
the smudge.
The smudge.
Maybe it has some relation
trying to
to
describe
the
the
smudge.
No, the smudge does something totally different, as I've said already, which is it doesn't have a third axis. There's no Z axis.
Okay.
So this is a Z
actually
axis.
like a Z. This
Yeah,
is it.
and
Cole,
complexity
I think,
is simply semantic density.
Yeah, I think in some way that's essentially what it will represent. And I think when I go through the example of the integration of these of the virtual and lab experiences, I think that will become a bit more clear in terms of what we mean with this added dimension of complexity.
One of the things that I've never found possible to achieve is to actually show a three-dimensional plane in any way, shape, or form that comes across well. So I'd be interested to see how you do that, because it's really hard to do that on a two-dimensional surface.
Yeah. Well, we'll see how successful we are in doing that. But yeah, so essentially so a holistic learning experience can be supported or achieved through two things. The one is transitions between the quadrants. So essentially these different mechanisms of engagement or learning activities. And then the other mechanism that we have is scaffolding in terms of complexity and building on essentially a scaffolding approach to reach higher levels of complexity in terms of engagement, in terms of insight. All right, so this the example that I'll show to just illustrate these ideas is essentially, the idea of transitions between the quadrants, scaffolding complexity, and achieving that through integration of virtual and lab experiences in the module that I teach. So just very shortly, just context. So we had traditionally in the control system module, we had a laboratory practical, so essentially position control of a motor that's driving a disc. And even prior to the COVID and remote teaching period, we actually developed a simulation model of that in MATLAB. So this is essentially what we call the virtual prac, and this is the lab prac. So we built this, essentially it's a replica of the physical system. So it's a simulation model of that, built it in MATLAB. We use Simscape for 3D modeling, Simulink for the control, and then the Simulink data inspector for generating plots. And then this is just some context on the lab prac. So this is obviously set up in a large engineering laboratory where we have up to, I think, 25 of these stations set up on these workstations that have power supplies, oscilloscope, programmable logic controllers, PLCs, some other peripheral devices with a PC. So just at this stage, what maybe I can just indicate is that this is essentially the view that the students have of the system in the virtual practical. So you can hopefully appreciate that it's quite clean, much less cluttered than essentially the real world problem. All right, so the laboratory practical, multiple components, there's wires going everywhere, there's a PLC, a PC, power supply. So there's a lot more detail in the real experience, in the lab experience than we expose students to in the virtual practice. So essentially this, we have this practical design assignment that the students have to do throughout one term of the semester. And we've then, what I've done, I've integrated the virtual and laboratory pracs through to basically build up this assignment. And there's nine steps essentially that we could break this assignment into, and I'll show you how we've mapped that to the epistemic plane with the idea that we've got this complexity axis added as well. So we start by giving students essentially a real world context for control problem. All right, so in the past we've had, they have to design the position controller for a remote camera tracking system to track players at Wimbledon. This year's problem is essentially how to do remote control of a water cannon to be installed on small fireboats in rough seas. So it's really a real world context for the control problem. Then we essentially give students the opportunity, and in the way that we structure the assignment, we also force them to think along the lines of what opportunities are there, considering the context of the real world problem, for applying the control theory that we've covered in the module up until that point. They then derive a mathematical model of the system, so essentially using Newtonian mechanics to do that. And then they've got this procedure where we've basically taught them this is what a controller should look like. These are the main components. These are the inputs and outputs. So they then design and implement a controller in that virtual practical setting. All right, so it's a lot of complexity is still hidden from them. The bridge is much shorter to go from what we've shown them in theory and in terms of the tutorials and in terms of procedures to actually implementing that. So they implement the controller in the virtual practical, and then once they've implemented that, they can then actually view the response. They can iterate. They can basically try to improve their controller to get a response that they can then compare to what would be the requirements of the system in the real world. So that's how, again, going back to, all right, let's put the solution that you've generated back into the real world context and basically analyze it in that space. Then the next step is then to actually look at the virtual practical and the solution that was developed in there in a bit more detail to identify what the shortcomings are here. Like, why would this work as a real world solution as it is? So it's essentially identifying opportunities to improve that solution towards something that is feasible in the real world application. Then step 7 there would be to perform a system identification in the laboratory practical to obtain an accurate model. So there they do a few experiments and update the mathematical description that they have of their system. Then step 8, they design and implement a controller in the laboratory practical. So that is now writing the code on the PLC and then actually achieving control on the real system. And then the last step there is to relate the response that they've captured from the laboratory practical, so from the physical system, and again comparing that to the real world context in terms of feasibility, in terms of satisfying the requirements of the problem. So yeah, that was the idea that we had, and this is how we've implemented it. So essentially what we try to achieve is to design this assignment in such a way that we guide students in transitioning between the different quadrants of the epistemic plane. And then what we can see with this spiral is essentially the idea of scaffolding. So if you recall that we've said that distance from the origin is essentially axis of complexity, then by structuring the assignment in a certain way, using this simplified platform, which is the virtual practical, before moving on to the laboratory practical, we can essentially scaffold the student learning, student insight to incrementally increase the complexity of the problem that they need to address. Yeah, that's all from my side.
Can I ask, so I'm thinking about how the various stages are put in one of the four quadrants, for example, number 8.
Yes.
Why is it ambiguous phenomenon? If you design and implement a control, so you already know what you're designing, you already know what you're implementing, so shouldn't that be stronger quantic relations?
Yeah, I think in that sense, there's a strong standardization to the approach. So they essentially have they know how to go from, let's say, the controller that they've designed, or they will design it in the S domain, using essentially a Laplace transformation to go from differential equations to the S domain, where they will perform their design. And then there's a standardized process to go from this S domain controller transfer function to essentially the equation that they have to implement as code. But the implementation of that code is then slightly ambiguous, in the sense that they are not sure how the system will react to that code. They're at that stage not exactly sure how the essentially from their perspective, at least, not understanding exactly what the internal workings of the controller and the software is that they are using. So that would be my perspective on that.
Okay.
Nikki has her hand up.
Thanks, Carl. One of the things I really like about this is your situational, the situational quadrant, where you talk about decision making. I think that's kind of in the engineering context, I think that's clicked something for me. And I think this last conversation is actually where I want to go, because to me, the reasoning of the spiral is imposed by principles. It's imposed by abstract theoretical stuff. Once you get to 7, 8, and 9, you're starting to bring in the technology of that. But my question is, where is the scaffolding of the technology? That I think, for me, one of the biggest shortcomings of an engineering education is that we don't speak about what things are and how they work. We speak about how you analyze them, but if you don't know what they are and how they work, that analysis is weak. In your example, you start talking about that at 7 and 8. Where's the scaffolding? Can you think more of that? Would it be a parallel scaffold, starting small and going out? How might one deal with the practicalities of technology?
Yeah, no, absolutely. And I think at least from my perspective, and what would be evident in the way that you can see my interpretation of achieving this, that would be the guideline here, is when, so in this specific case, it's working with that physical setup, working with the software that's involved, working with the controller. And to really be effective, one would have to follow the same approach, incrementally, incrementally introduce complexity in the way that students engage with that. I think that the challenge then just becomes, and this is something I think we can all appreciate, is just how valuable a resource time is, and how much we need to optimize that to actually cover the ground that we want. So hopefully, one would also have to look at this from a entire program point of view. Does the program allow scaffolding in terms of technologies? Is there a continuity in terms of technologies? One example I think that we have here is possibly MATLAB, where I can assume that students that once they reach my class, they've had at least 2 modules where they've engaged with MATLAB to a certain degree. So I can assume that they are already at some entry threshold where I can build from to build up to higher, more sophisticated understanding or more complex problems.
I'm just also cognizant of the time, Carl. Thank you so much. Nikki, I was going to say, so we've got our paper. This started in semantics. And so we've got a really nice paper. I'll put the link in here because you can download a free copy of using the semantic plane precisely on scaffolding the technologies. I'll put the link in there. Nao, do you want to present yourself? Okay, go for it.
Please let me know if you can hear me. I'm just trying to find the right screen on this side.
Okay.
There we go.
And
is it showing?
You're right at the beginning. So just
sorry.
Cool. No worries.
Okay, so that's
there we go.
Where I am. Can you see my mouse pointer moving around?
Yes, we can.
I should maybe try and make it red. No, it's fine.
It's fine, we can see it.
Yeah. So what I wanted to talk about today was looking at our students themselves. So our knowers that are sitting in our classes and looking at how they go on transitions or some kind of autonomy towards type of trajectories on the epistemic plane. The work that we did was in collaboration with Robbie and Corin in the fluid mechanics module. And the approach that we took was very similar to how a lot of Corin's work, a lot of Corin's PhD work, where she engaged with professional practicing engineers, asked them of a recent problem that they had to solve and asked them how they approached that problem. We gave our students a specific problem to try and solve, and that was to simply go and look anywhere in the world around them, identify some application of fluid mechanics, and describe that. So describe the application and describe any fundamental principles that they're learning about in the fluid mechanics module that they see at work in the particular application, and in their explanation use as many graphics, equations, theory, etc. as they seem appropriate. And afterwards we asked them in a survey to describe how they approached that task, and from that feedback we could try then figure out how they went about code shifting on the epistemic plane. We ended up plotting the trajectory of each student on a epistemic plane, similar to the plots that Corin showed earlier on. And specifically, we were looking for a couple of things. We were looking to see in the student's description of how they went about approaching the task, are there clear evidences of the student moving through different codes, so clear instances of the student engaging with insight from the different codes. What's the pattern that the particular student seems to take? And beyond that, does it look like each student has a preferred insight that they like engaging with? So do we have students that prefer speaking to the stakeholders, for example, that are affected by a particular problem, which would then sit in the Noah quadrant? Do you have students that prefer to first go look at the textbook, identify a couple of phenomena, find the one that they think they understand the best, and then from there try and choose an application that suits that, which would be somewhere in the purest quadrant? And if we do find that a particular student seems to have a first preference for one of the codes, from that description, does it look like they're able to easily transition and move along the entire epistemic plane? Or does it look like if they try to move from the right to the left, there's a little bit of a frustration or intentional? I think, Pavel, you spoke about a resistance earlier, for if our students come in with a preferred insight or preferred way of looking at things, and we want to expose them to other ways, is there a little bit of a resistance? So we're trying to see, is there any wording at all in the answers that suggests some kind of resistance, whether it's moving from somebody that's either on the situational lower quadrant to somewhere on the right-hand side, or someone that's on the purist or doctrinal quadrant and they want to move to the left-hand side, or maybe someone that's in the top going to the bottom, etc. We called that kind of resistance a code clash, meaning that somebody, for example, that prefers a situational quadrant, which is very weakly bounded discursive relations, has a bit of a resistance or a clash when they're trying to engage with the more purist or doctrinal, stronger discursive type of relations. And we took a sample of our students that had completed the task and completed the feedback. From that, we analyzed about 18 students, plotted their trajectory on the epistemic plane. From those, there were multiple types of trajectories. The most obvious two categories we could find was students that seem to indeed engage with at least 3 or 4 of these quadrants in a non-linear way. For the specific first student, for example, they would start up in the doctrinal quadrant, go to the Noah, go to the doctrinal, go to purist, situational, doctrinal, and back to situational. So there isn't a fixed way of navigating this. And they seem to comfortably engage with all 4. And the students seem to prefer the situational quadrant from the way they answered the problem, the way they answered the survey. So we assigned them as somebody who's fitting in the situational code, and then we said that they don't have a code clash. A second student who also preferred the situational quadrant seems to indeed have some code clash. And when we look at how they answer the approach, it seems that they first started out in situational, went straight to the doctrinal, and then didn't go anywhere else. So they pretty much engaged with just 2 quadrants in a very linear way. And we wanted to do this because from Corin's results looking at professional practicing engineers, it seems that the better engineering problem solvers are able to easily navigate all 4 quadrants and problem-solving opportunities. So we want to see our students that we want to, when they graduate, to be able to indeed solve real-world engineering problems. Will they be able to easily do this at this point, halfway through their degree? How far along are they there? And if we were to now go back to Robbie's presentation from a pedagogical point of view, design a curriculum, how could we structure certain modules at certain points in the program to enable better code shifting for all our students, regardless of their preferred insight when they come in first year? For these particular students, we were analyzing the results when they had already passed the first 3 years of the program. So we had the benefit of being able to correlate whether they have a preferred code or whether they experience a code clash with the final mark for the module as a percentage, as well as the average of all the modules that they'd had in the first 3 years of our course. So we did that for all 18 students. And we do find a link between what we thought was the preferred first code and what the average mark tends to be either for the module or over all the first 3 years at least. The colors here correspond to the same color quadrants as on the figures on the left, and the gray is just the average. The solid colors is the mark for the module. The faded out is the average for the modules in all 3 years, the first 3 years. So with a scale going from about 50% to 90% on the y-axis, it looks like those that have the purest preference tends to do better in the module as well as in the first 3 years. The group that performs the second best seems to be the doctrinal, and that would make sense since a lot of our modules in the first 2 and 3 years are strongly situated in this purist doctrinal space, where we teach them fundamental engineering and science principles. We teach them certain methodologies that they must apply, for example, how to differentiate an equation or how to integrate an equation. That's a standard procedure that everybody must be able to follow. And it seems that those that come in first year already having a way of thinking that better aligns with the strong discursive relations do better. the situational and no-orientated students that prefer the more open-ended or more weakly bounded discursive relations tend to do a little bit poorer and even a little bit poorer in the average in gray. And that is consistent for both the final mark in the module as well as the average over the first 3 years of the program. The idea is that by the time they get to the end of a third year going into the fourth year, they'll be more comfortable with open-ended problems such as the capstone design project that they have in the final year. And so it would be important that potentially maybe in the first 2 to 3 years, we make a point to help the NOAA and situational orientated students code shift better when they come to the right-hand side. And then in the fourth year to make sure that the purist and doctrinal students now who are very strongly on the right-hand side don't struggle going into the very open-ended capstone project in the fourth year. And then we found a link between the marks as well and whether we thought there was a code clash or not. So the code clash is the person that is very happy to stay in the little preferred code, but they struggle going to the other side, especially if it's moving from right to left or left to right. The students that we thought did have some kind of code clash are in yellow. The solid is the average mark for the module. The light is the average mark over the first 3 years modules. And those with indeed a code clash in the yellow tends to do a little bit worse than those who couldn't quite see if there was indeed a code clash or not. So I've labeled that as unclear in the pink, and the blue are those that we thought didn't show any signs of code clashes at all, such as this first student that I've plotted here. And those students seem to do better on average in the module, as well as the first 3 years of the program. So that's what we've been able to see in our module, at least when we now analyze our NOAAs and try to figure out what preferred code shifting strategies do they show. And if we compare that to our marks, it seems that the students that come in initially preferring very open-ended, very unstructured ways of doing things may struggle more in the first couple of years of the program as we teach them the very fixed principles and fundamentals and very fixed methodologies of doing things. At the end of this year, this particular crop of students would be at the end of the fourth year, at the end of the program. So we'll see if these results are still correlating to either the average mark over the fourth year and even the mark that they will receive for the capstone design project, which should be more open-ended.
Neo, can I ask a quick question?
Yes.
I just wondered if we think in terms of like Bourdieu's habitus or Bernstein's coding orientation, how fixed or flexible are the students? So over time, so you're talking, it sounded like you were talking in terms of coding orientations, that whether somebody is a natural code shifter across the plane or whether somebody tends not to and they shift directly to the doctrinal quadrant or whatever. Is it trainable? Do you see students who are sort of perhaps slightly more linear in first year, by final year, have they become better code shifters? Or do you find that actually in terms of habitus, in terms of, is there an engineering DNA that is actually quite hard to change, or the sort of the kinds of spirals that Carol was talking about before? Does that curriculum logic and those approaches and those ways of scaffolding students across the plane actually begin to shift their coding orientations?
I think that's a very good question that I've started a conversation with Karen on that's still going to continue. My honest answer is I don't know. I think to some degree, and that's what we're hoping to be able to tell by the end of this year, to some degree, it may be that the fourth year, which is supposed to be more on the left-hand side, more open-ended, there may be still significant elements of that fourth year that are still very purist and doctrinal in nature. And that the students that started out doing well with the very doctrinal and purist type of knowledge in the first and second year continue to do well, because through talking to people, they are still able to find kind of like a tried and true way of tackling the capstone design project, which is supposed to be open-ended, so that it may not end up being as open-ended as it should be, and that we can't yet figure out, have we taught our students to truly be comfortable moving all over the epistemic plane. The other comment, I would say, using myself as an example, who's very much a situational type of thinker, I've wondered as well about myself, saying now 10 plus years post graduating and having now dealt with a lot more problems, where would I put myself? And I find myself thinking that I'm still very, very situational. In many cases, I seem to first go situational, then purist, then go back and forth between the two. And it looks like on the surface, I'm better at code-shifting over all folk codes. But to be honest, it may be that I've gotten better at leveraging the people around me that are better Noah inside people or better doctrinal inside people, so that I pretty much am still in situational. It's just now I have the benefit of being in a team that has all folk codes represented. So
Can I also jump in there? So Steve, your question is, is there like an engineering DNA? Are our students coming in able to deal with situational problems? And the answer is no, definitely not. They
because we don't choose them.
Yeah, we don't choose them on that basis. We choose them on do they get 95% for mathematics at school and that kind of thing. And it is definitely a development. I mean, Nao's points that she's been saying now is she tends to still have a tendency towards situational thinking. And I think there probably is a tendency, like as the kind of person you are, but is it trainable? My intuition, I don't have any data for this, but is it trainable? Yes, it must be. Otherwise our students would not pass their final year design, because it is 100% situational, and they have to then draw on purist and doctrinal to solve it. But it starts as situational, so they wouldn't be able to pass otherwise.
Yeah, thank you.
Karen, I think you wanted to.
I was going to say, I was cognizant of the time now as well, and we had this question that arose, and you can leave the slide on there, Nao. When Nao saw Carl's planning, and when we sat back and looked at all this planning and the design of what we're doing, Nao mentioned to me in conversation, I don't think I'd be able to learn like that. I don't want you to fix my journey. And it rose the question of what we put in this short blurb for this roundtable of, okay, so here you've seen us take one instrument, and we have used others. In terms of the complexity issue, I posted the link, and there are lots of free copies because it's 4 authors on the semantic plane paper. I put the link into the chat, just to, especially Carl's and Robbie's, in fact, work of fleshing out what this is in terms of the semantics, But I think we've all realized, well, now we've got these lovely models and these plans and these trajectories and this forced code shifting or movement. What does that do for different kinds of knowers, or for people with different kinds of insight orientations? We've been calling it that. And I thought, how far do we push the design of this while being cognizant of precisely the conversation we've just had? We draw students in our program that are strong in maths and science, full stop. And then we cry because industry says, why can't they solve more complex open-ended problems with greater Noah orientation? All the soft skills complaints we get about engineering are precisely because of the inability to code shift or to recognize and engage with the kinds of insights that are required, let's say, on the more open-ended left-hand side of the plane. I don't know how much we can force them that way when our program is so solidly anchored on that right-hand side. So I just wanted to throw that out there. Any other insights into, does one fix the design of this and for students? How do we open up
If you think about it, I mean, I'm thinking aloud, but if you think about it in semantics terms, and the way that for certain audiences, given your understanding of who they are and what they need, you might start high and wave down. So you start with principles and theory, and then you contextualize with case studies. But so that might be working with researchers. If you're working with practitioners, you might want to start low with the context, with the problem, and you wave up. So if you're thinking in those terms, for something like this, it would suggest that if you're empirically seeing that different students have different tendencies, then that suggests that they might need to start in different places.
Yes.
So in terms of curriculum design, rather than saying, well, our major problem is that people can't shift from the right to the left, it sounds like you've got students that may have problems in both directions. Yes. So for curriculum design, it might be about designing trajectories through the curricula that allow for choice. So you can't know what coding orientations your students have, but if you know that you're introducing variety and diversity in the way that they tour across the plane, then you know that some of the time you're hitting those different starting points that are going to align with student coding orientations, and some you won't. But on balance, everybody gets the opportunities to start from a comfortable space.
Yes, that's fantastic. I mean, practically in the large class context of our 1,000 first-year students all being taught by 4 lecturers who have maybe 250 each on a fixed, this is in the syllabus, this is what you'll cover this week. They're all doing the same tutorial, but they divided in first year according to language, and which also brings other sorts of things into play. So you have caught between a rock and a hard place in terms of how you do that in that context. I'd be interested, Robbie, I mean, I'd be interested in your insight on how you open that up for those large class first years.
With great difficulty, but it doesn't mean it's not worthwhile doing. I think it's not as important in first year. I think as you move up, then it becomes much more important, because the first year is, in fact, the first 2 years are just, it's just basic stuff. So it's kind of just get on board with it. And if you can't get on board with it, if you can't do the stuff on the right-hand side, then you're unlikely to be successful in studying engineering, which is maybe a little bit of a hard-ass way to think about it. But yeah, are there ways to have both directions? Well, you know, the kind of project that Nao put together for our foods module is an unusual way to think about it, and we had some really good results from it, and we're definitely going to continue doing it. So, you know, we just have to think about these things with a bit of creativity. Much easier in smaller classes. Big classes make everything.
Yeah, I was going to say, is there scope for thinking about kind of recontextualization from you know, into classroom? The curriculum is very hard to shift, isn't it? It's a kind of it's a big liner ship that if you want to change direction, it's going to kind of happen very, very slowly. Whereas
curriculum change is basically impossible exercise what we do, but what
recontextualization,
how we do it,
recontextualization into the classroom.
That
means that within, you know, even if you're in situational quadrant within the curriculum in the classroom, you can shift it to principles. If you're in principles and you're dealing with theorems or whatever it is in the classroom, you can shift that into thinking about real world problems and opportunities and so on. You know, is there an opportunity? Maybe that's what happens already. That in teaching, you're able to tour in order to create those opportunities for the different students to make those connections.
I think one of the, as much as the curriculum itself is fixed, one of the more flexible components is these assignments that we give to students, including the one that we give to the fluid mechanics students. There's a paper that Lydia Oret and Karen worked on a couple of years ago, where Lydia looked at the big assignment that's normally given to the students towards the end of the semester, assuming that at that point they've gone through the fundamentals and principles in the module, and then they are now able to apply to this big, more open-ended assignment. And what she did is that she gave the students, she rolled out the assignment right at the beginning of the semester, And as she identified certain parts that would need certain information or certain knowledge that she was teaching in the class at the time, then she'd bring it in during tutorial periods. They wouldn't necessarily work on just the textbook problems, but they would also work on parts of the assignment that feed into the module content being covered in the lecture at the time. So a bit of a scaffolding approach, similar to what Carl was describing just now, but where the assignment, which is a situational open-ended contextual problem, is not standalone from what is being covered in the more purest doctrinal nature of the classroom, and instead they go hand in hand throughout the entire semester.
I've got a question. Oh, sorry, Nikki, go on.
So Nikki's had her hand up forever. Mike.
So it's fine, because I do want to shift the conversation to, I want to ask that ontic relations, discursive relations in a different way, but I think people are talking specifically to these presentations, so I'd like to rather go to the end.
Okay.
Okay.
Also, I am watching the times, but carry on. Carl, we're relying on you to tell us when we need to stop. Go for it, Pavel.
Well, I'm just allowing the conversation to keep going for a minute.
So I've got a question, which is a reaction to a couple of points, including mine. So Robbie said that in years 1 and 2, students very much stay on the right side of the plane, right? But in year 4, they have to move into the situational inside quadrant, because otherwise they're not going to pass, right? Then Steve mentioned Bourdieu's habitus, right? So within the first 2 years, you're also instilling in them the engineering habitus, right? Then before then, I ask about whether there is any resistance. So the question where I'm heading to is, if you after 2 years suddenly change the rules of the game, right? Then I suppose resistance goes up, or some students won't make it because they don't recognize that rules have changed. So how explicit are you about this change from the right to the left?
The hope is that the lecturer is explicit in saying, for a specific context or a particular module topic that they're teaching, that they will draw in the right-hand side type of knowledge that the purist, the doctrinal students should already be familiar with, and then start explicitly showing how it may affect different contexts or the different assignments that they'll be working on. I just anecdotally, going from what I've observed, I think most lecturers who are not as exposed to some of us might be to the LCT space are not aware of just how explicit they must be in the communicating that. Because us sitting on this side who have been lecturing this content for a very long time cannot easily see the links between different sections, and it's implicit to us. But for our students, to them it's new, and if we don't make it explicit, they will not see it either. So it would be very important for the lecturers to make that explicit, but the lecturers themselves first need to recognize the need to make it explicit. Else we work with assumption that a student that passed first year has mastered everything that they were taught in first year, and we can now immediately start teaching them second year material without actually checking, does a pass mark of the first year fundamentals and principles necessarily mean that the student is now ready to be taught second year things, or should there still be some kind of bridge or transition or some other means of the lecturer making that transition explicit? Same thing when we go from second year fundamentals and principles and we get to the third year more open-ended situational contexts.
I was kind of wondering whether you make it explicit from year 1, right? That there are going to be these shifts or these tours so that students are ready and they're not like, okay, now there's a change. Oh, year 3, oh, another change. Year 4, yet another change.
I think from that, I have one sample case that I can report on that I know of. At a different institution, they have a extended degree program similar to what we have, where the students are given 1 extra year to complete the 4-year degree. And in that particular program, what they've done is that in the common first year, they don't necessarily allow people from the maths and science faculty to teach the engineering students maths and science, but they've gotten chemical engineering lecturers from the department to teach them the maths and science. So as the chemical engineers teach them maths and science, it's easier for them to start bringing in the material and energy balance context or the heat exchanger design context that they will be encountering, so that in first year, when they teach a first year student how to integrate or differentiate an equation, they say this is the same way that you'll be applying to integrating and differentiating the Navier-Stokes equation in fluid mechanics when you try to size a pump or size a vessel, for example. So that has worked well for that specific department at that institution, but the norm is that first year engineering students are taught maths and science by lecturers from the maths and science faculty and not necessarily people with the engineering background. So it would be a little difficult.
I see Carl, and I am also watching people leaving. And Carl has her hand up. I'm assuming Nikki's keeping a question for last. I was just going to say, we've just come back from a retreat around our program renewal initiatives, where this whole issue of who's teaching what and how it enables code shifting into greater complexity has meant that we've actually pulled in those lecturers. So we've got the physics lecturer from the Faculty of Science and the mathematics lecturer from the Faculty of Science, and have engaged them in our REAP projects, and they're working on enabling each other to see. And it was really, really productive for our engineering lecturers to work with these two lecturers to actually see what they hadn't seen before, to enable better, the making of these things more explicit, and to enable like improved code shifting over time. Carl.
Yeah, Corinne, just on Pavel's point and what Neo said there, I think, and I've also discussed this with you, I think a big weakness in our engineering education, especially our context, is the fact that in the first and second years we tend to only essentially engage students in the purist and doctrinal quadrants, and we should be moving to an approach where we basically have that shifting across to all four quadrants, and maybe in terms of just my interpretation or my addition of the plane with that complexity axis is to actually at first and second year levels, essentially your distance from the radius should just stay small, because that is, in the broader sense, that is scaffolding. And if you can do that transition and keep it, simple, and simple is obviously very relative here, but keep it simple and basically grow that spiral over the 4 years, I think we'll be much better off.
Yeah.
We need to wrap up in a second. So was there something from Nikki?
Yeah, I wanted to just ask, Carl, I take your point that you can't compare dimensions. And I think that's really useful for me. But I'm still...
Well, I didn't say you can't compare them. I mean, you can use them together.
Don't conflate
mix them.
But don't try and, don't turn them into Frankenstein's monster, because they're fundamentally different. So, for example, you need a target to be able to even begin with sovereign code. So when somebody says, oh, that's close to the sovereign code, I think, yeah, you've got a tacit target you haven't defined, and I don't know what it is yet.
Okay, I'm not following you entirely, but...
You can't define any of the codes in autonomy without defining what the target is first.
Yeah.
Okay, so but my question here is, I'm very intrigued, the axes in each of these. So in autonomy, Karen, you've used it on the epistemic plane. I've used it on for semantic density. We're working on the same idea of SD, SR and OR. And I'd be really interested to understand how those axes, how those axes are similar and different when you use them on different dimensions. I take the point that they're different. They must be different. They must be doing different things for different purposes. But at some level of a conversation, sorry for my light, at some level of conversation, I'd be very intrigued to understand how they play out differently in these different dimensions.
Okay, I'm going to say that I think we should park this, because Jack and I, is Jack still on? Where's Jack? There's Jack. Jack and I have been battling with this for 3 years in terms of capturing different facets of knowledge practices. In other words, looking at, we're looking at assessment. and looking at that. And every time in our conversation, because we speak LCT, we pull in this dimension, then we pull in that dimension, because you're looking at multiple facets of, let's say, a larger problem, but it makes you zoom into something. I think what Nikki was trying to say around the autonomy plane is that in a region like engineering, or let's say, what's happening in the purist quadrant, the purist insight is dictated by a field that has agreed consensually on the nature of, description of, or value of a particular phenomenon. All those natural sciences stuff sits there. So in other words, I think maybe, Nikki, in your head, you're going, all right, the practices around that phenomenon are so strongly bounded. They've grown very much the hierarchical knowledge structures stuff. They've grown through consensus over time to be this body. And when you see knowledge practice engagement with that particular body, the purist insight is evident. You see it. Hence the fact that across textbooks around the world, thermodynamics will be exactly the same, irrespective of how they choose to lay it out, etc. And when you see practices engaged with in the appropriate way, it looks like, in terms of autonomy, sovereign. In other words, that it's from a sovereign position. The whole field agrees on it.
There's the alarm going off, right? Because that has nothing to do with sovereign code. You've
But
just assumed that that's the sovereign code, because I can tell you that if your target is some other thing, not that, but some other thing, then that's not the task. That's not the sovereign code. So like this is the point. It's got nothing to do with like the consensus or there being like a large number of people all doing the same stuff.
Yeah.
Nothing to do with that.
But I mean, if your target were the engineering core knowledge and associated practices from an autonomy perspective.
We can't, but you can't assume that.
Okay. But I'm saying if it were, I'm just thinking, Nikki, that maybe it's around that. I don't know, that you're thinking of autonomy.
I think it's
who says what counts.
Yeah, I think it's a different discussion. I think I find it very interesting to engage, Carl, with what to really understand the different dimensions. I think this kind of making sense of it myself. You're using the same axis names. You're talking about different things because they're different dimensions. I think it would be interesting to get my own head around that.
I don't think they're the same axis names. It's just that because we're relating two things, it's about relations. I mean, you could do this with anything. You're going to have stronger and weaker relations. We can go out of LCT and put two things together and then look. So I'm just saying it's because of the Cartesian basis for relating things.
That's not quite what I'm getting at, but I think we've run out of time.
I didn't get the thing about the same axis names, because none of the axes have the same name.
Yeah.
Sorry, I just mean ontic and discursive and the foundational meaning of ontic and discursive and whether they're being used similarly or differently. And I need to spend more time on that. I think
it might help just to quickly note that there's no concept called ontic in LCT, but there is a concept called ontic relations, which has a definition to it. So, and that doesn't drag in any other meaning for ontic that somebody else might have on its own. So we just have, like, I don't know, we'll have a conversation. We can have a conversation. One of the great things about this is that it flags things up that we can then go on to dig into and have a good discussion about later. So that sounds like the sort of thing that we might want to have a session just on those sorts of things, like a sort of theory session of some kind in which we can get into this sort of stuff, which we can set up anytime, like we can have we have different names for various things. Like we could have a live and online kind of session where we can get into things like dimensions and various other stuff like that. How does that sound?
I would really love it. Yeah.
Awesome. Yeah, no, that'd be great, because like it's only that way that, I mean, until I get this book that I'm currently writing done, which could take me 300 years, I am being the slowest writer on earth. It's there's so much I've come to realize while I'm doing it. There's so much that isn't yet written down and clear on a kind of fundamental basis of, you know, these sorts of things. That so yeah, the more chances to be able to talk those things out would be really useful. You know, and also what's not clear and what's clear. It's like, it's really obvious that some things are really clear to me and they're really not clear to anyone else. That's a major failing because I haven't made them clear. So, you know.
Yes.
Thank you, Corinne. And who else did we have? Robbie, we had Nao, we had Carol.
Yes.
That's all of them. Excellent. I've got them all. Thank you guys so much.